Welcome back to our lecture series in engineering mechanics, for which we are starting a brand new chapter today, because we are ready to move on from force vectors in 2D and 3D. We have a very solid understanding of those concepts now. So now it's time for us to talk about equilibrium of particles before we move on to the next chapter, which would be equilibrium of rigid bodies. But before we run, we need to walk. So let's talk about equilibrium of particles. And I think it's a good idea to talk about these terms before we actually move into today's objectives. So, of course, most of us already know what equilibrium stands for. But just for all of us to be on the same page, let's understand that we talk about balanced systems here. And for most of us here in the class, that means that we're talking about static systems, systems that are non-moving and that are completely imbalanced. So they don't move left, right, up and down, or in any other direction. They are in equilibrium. The one that is probably a little bit more important to define from a conceptual understanding standpoint is the term particles, because particles can be so many things. Like we all know particles in space and other definitions of particles. But here for us in engineering mechanics, what we're talking about are objects with mass but with neglectable volume. And let me explain this a little bit. So we definitely need to emphasize that we have mass in an object, because that is the mass that we're trying to balance. But we're using a trick here in engineering mechanics, and that is we neglect the volume, or we ignore the volume, which of course is not true in real life situations, but it is a trick that we use because we can. And because we can means in this case that the volume has no impact on the type of analysis that we are conducting. So, for example, if we look at a very famous cable structure that we probably have seen in our lives here and there in many American cities, we see, let's say, traffic lights which are hanging from cables, and of course I'm idealizing this here, but let me draw a little cable structure with a little traffic light here, and the traffic light is, let's say, mounted to a wall here and a wall on the other side. And if the engineer wants to know more about how much force is acting in a particular cable, so let's say I want to know how much force is actually acting in this cable here. So of course we know that cables must be in tension. We'll talk more about this today, but there's tension in this cable. And then we have tension in the other cable, and this is not a proper drawing yet, this is just an introduction. I will properly define this for you throughout the lecture. But we have tension in this cable, and then we have tension in this cable. And of course there's tension in the other cable as well. Let me add that, of course, just to be complete here. So you have tension here as well. However, for the purpose of calculating the tension in these cables, the engineer could not care less about what's hanging here. The only thing the engineer would care about is what mass does the object have that is hanging here. So it doesn't matter if it's a traffic light, a lamp, a box, whatever you want to think of, it is not important. The only thing that matters is how much mass this object has. And therefore, we can actually talk about the equilibrium of particles, and particles only for now. Of course, we're going to do this in 2 dimensions first, so that we can prepare ourselves properly for the upcoming 3 dimensions. But we are now ready to tackle the objectives of today's lecture, now that we understand what particles are and where they are used. So first, I want to introduce to you the general concept of that equilibrium and where it's coming from. So that then later on, very shortly after that, I can define the equilibrium conditions and the equations. And that is very important that you understand the difference between the two, which is one goal of today's lecture, to clarify that to you. And when you talk about equilibrium of particles, you need to also combine this with what's called free body diagrams. We will therefore define what free body diagrams are and what all the necessary components are that you have to include in all your free body diagrams so that you can receive maximum points and of course communicate properly and effectively with other engineers. That's the real goal here, to understand how we do that in the future. Ultimately, the purpose of this lecture is to teach you how to calculate the tensile forces in simple cable structures, similar to what I just showed you above here. So we actually have an example like this today, where we can calculate how much force is acting in these cable structures. So without further ado, let's get started and talk about the concept of equilibrium. So the general concept, first of all, as I said before, is that we're talking about balanced systems, right? So we need balance. So balance is a must. And what does that mean for engineers? That means that the Newton's third law really applies. So we're following Newton's third law, which really states that action is equal to minus reaction. Let's talk about this for a second. Of course, you learned this in physics before, but let's take some everyday examples. If you sit on a chair, you are the action pushing down. The reason you're not falling down is because the chair is reacting to you and is pushing you up. So together you guys are in equilibrium. Or take, for example, riding your bicycle. If you ride your bicycle, you make the tires rotate, you pedal, and that's where the first action-reaction comes in, where you pedal. But then the tire hits the asphalt, and because there's friction between the asphalt and the tire puts an action on the asphalt, and the asphalt reacts to it, and therefore the bicycle is moving forward. But of course, here in engineering mechanics, we deal with static systems, so things that are not moving. And let's just have one more example of action minus reaction. So let's say you have a house that sits on a foundation or on the ground. So let's say here I have a ground. And then let me complete my house here. If you haven't noticed, I'm a fantastic artist. That's why I became an engineer. So here's my house. Let's say there's a door here. And of course, the house is pushing down on the ground with whatever that house has as a weight. But then the ground is pushing back on it. And only if those two forces are in equilibrium, your house will stand still. And that is obviously what we want, and that is what we want to prepare for as engineers. So the concept really translates to the sum of the forces, or summation of all forces, must be equal to 0. And that is the general concept of equilibrium. Of course, this applies in any direction, right? So this is true in all or any direction. Of course, as mathematics people or engineering physics people, we always try to think of vertical and horizontal or X and Y, which of course we're going to go to today. But you have to understand that this concept has to apply in any direction. So, for example, if I push on my house with wind, right? So let's say there's wind pushing there, then of course the roof needs to push back in the opposite direction to keep equilibrium. And this is very important to understand, that we're talking about any direction here and not just an XYZ direction, because otherwise the system would just fail in a different direction, not necessarily the XYZ direction, but in a random direction. That's why in this class I will also always stress that you understand as a beginning engineer that a coordinate system is really not something that needs to be horizontal, vertical, or something like that. It is something that the engineer defines. So for example, for my roof, maybe it would make more sense to define my XY coordinate system like follows. So there is my y-axis, and then here is my x-axis, because that will make my wind analysis easier, for example. That is a topic we'll cover later, but you have to understand that the general sense here for the forces to be in equilibrium, or the net sum of the forces is equal to 0, that must be true in any direction, not just in x, y, or not just in one direction, it's true in all directions. So now we're ready to tackle the equilibrium condition, and the equilibrium condition really states exactly that, except in engineering terms. So we would say that the sum of the forces in any direction is equal to 0. But this would of course be too much writing effort for engineers, so engineers actually like to break it down into an x, y direction in 2D. So remember that here we're talking about 2D. So engineers would state something like the sum of the forces in x is equal to 0. But that is not good enough. We also have to state in which direction it's positive. So please get used to this now, that from now on you write the positive direction. So plus with an arrow to the right side is how I define positive. You may have written this equation before, but you may have not done this part. So this is important from now on. Similarly, for the y direction, so the sum of the forces in the y direction is equal to 0. And of course, I just assume that everything that's going up is positive. Let me prepare you for something in the future here. This does not mean that it corresponds with my coordinate system. Yes, it is true that in a regular coordinate system, my x-axis usually is horizontal. Let me draw a coordinate system for you here. So I do have an xy coordinate system. X, y. And of course, we know that this would be positive in this direction. And for the y direction, likewise, if it's pointing up, it's positive. But that is not necessarily what this condition states. What this condition states is that in my equation that I'm going to write down here for you in a second, in the equation that is coming up, everything that's going upwards, I, Raphael, consider positive, which of course corresponds with this. However, I could flip this around and then my equilibrium condition would still be true. So alternatively, I could also write that the sum of the forces in the x direction is equal to 0, and then I could state that everything that points to the left is positive. That may sometimes be helpful. Likewise, the sum of the forces in y is equal to 0, and then I would state that everything that's going down is positive. But this will more or less depend on the case that you're actually dealing with. So let's not worry about this for now. Just understand that these conditions here are not equivalent to saying that my positive y values in my coordinate systems are upwards and my positive x values are rightwards. That is not what this states. It just states how you're going to use the equilibrium equations. In fact, let's move on to the equilibrium equations now. And let's first draw a coordinate system that we can use as a discussion base. So I have an xy coordinate system here. And within that coordinate system, I'm going to place 2 or 3 forces. So let's put some different forces in here. Let's call this F1. And let's put an F2 in it. And maybe for educational purposes also a F3. Of course, we already see or understand that each of these forces can be broken down. In fact, that's why we talked about this stuff at the beginning, the vectors. So let's break it down into an x, y component, each one of these forces, or at least two of them. I don't need to steal your entire time with this. So this here would be f1y, and this would be f1x. And I can also do it for f2. So let's do that. The vertical component needs to be included too. So this would be f2y, and this would be f2x. And of course this is true for f3 as well, but I'm not going to steal your time with that. So that I can now explain to you the equilibrium equations, which always have to be preceded by the equilibrium conditions. So let me start by saying that the sum of the forces in the x direction equal to 0. And then I need to, of course, include my definition here. I say that everything to the right is positive. And the very important thing now is that you separate the equation from the condition. So this is the condition that you see right now. And now I have to restart my equation from 0. So 0 would be equal to plus f1x minus f2x plus f3x. And let's look at this. So f1 is pushing to the right, which is per my definition here positive. So therefore it's positive. My f2x is pulling to the left, therefore it's negative, and my f3 is going in this direction. And you could substitute values now if you want to be really convinced that it makes no difference if you write it this way or this way. So a little side note here, so let me write this completely in green. If I were to say sum of the forces in x is equal to 0, and I were to do it in the other direction, of course I cannot forget my colon here, 0 would be equal to minus f1x plus f2x minus f3x. And the reason I'm writing this in green here is because I don't want to confuse you with the color choice here. So this is really true to this picture here, whereas this one is just a different interpretation following this notation. But now, again, convince yourself by plugging in values here, and then understand that if you use the same numerical values just with different signs here, you will come to the same conclusion. You will find the same answer. So this is true and this is true. And that hopefully convinces you that this sign is not related to the positive x-axis. This is what you use to define your equation here. And so let's actually write that down. So this portion here is actually the equilibrium condition. Whereas the part here on the right, that is the equilibrium equation. So now that that is clear, let's also complete it for the y direction. So the sum of the forces in the y direction is equal to 0, colon, and my positive direction is upwards. And now I can state that 0 is equal to plus f1y plus f2y minus f3y. And I want to point out one more time how important it is to separate this component from this component, or the condition from the equation, because often I see this incorrectly, and I'm going to use a yellow color because you actually shouldn't even see this, but sometimes students write the sum of the forces in the y direction is equal to 0 is equal to f1 y plus f2y minus 3y. And that is incorrect on so many levels, so let's go ahead right away and actually cross that out. But I want to make sure that we understand this even here through remote teaching, that this is incorrect and cannot be accepted. You will always lose points for not separating the conditions from the equations. So please understand this. And maybe for our notes, one last thing here before we leave this page is to say that this here is the alternative. So now we have a solid understanding of the concept of equilibrium and what that means in 2 dimensions. We also understand the equilibrium conditions and we understand the equations. Notice that we had to develop these equations based on this picture here, which for now you can consider a free body diagram, but it is not following all the rules of a free body diagram. So our next step would be to define really how a proper free body diagram has to look like to communicate effectively with other engineers and to get full points in this class. So let's move on to the next page and talk about free body diagrams. I'm very certain that most of us have talked about free body diagrams first, or at least took classes where you needed to define free body diagrams and also complete them. However, I learned through many years in the classroom that some students have a different understanding of free body diagrams than others. So therefore, it is my goal to define them here on this page and to explain to you what we really need in engineering mechanics. Every time you're looking for full points on a problem where a free body diagram is requested of you, you need to have all the proper tools and the proper definitions in place. So let's get started and talk about that. So number one, the free body diagram is really a representation of a physical system, right? So it's a representation of a physical system. So therefore, you have to reflect reality. And that means you cannot leave anything out, right? So you cannot ignore important components. So let's say, for example, you forget a cable. In real life, the structure would fall down. So that is not acceptable in a free body diagram. And what that really means for us in the class is that we have to include all forces acting on the system. So must include all forces acting on the system. And all is a very important term here. So that means that you have to include all known forces but also all unknown forces. That means you have to develop a solid understanding of what is going on in the system. You cannot just add what's there, which would be the known forces. Much more important, you need the unknown forces. And of course, I will describe this to you when we go through an actual example. You also need to include all force components. So that effectively means that you have to include the X components, the Y components, and if we talk about 3D, the Z components. So in other words, we're talking about the 2D description here and the 3D description here, That is, of course, not a secret to you. But these components take us to the next important aspect of these free-body diagrams, which is proper naming. So all of these components and everything you put in a free-body diagram has to be properly named. So each component must be named. In other words, you talk about your x, y, z components. So let's say you have f1x, you have f1y, that needs to be clear where that is, and maybe even f1z, etc., etc. So that's the naming. Besides the name, you also need to include the direction. So clearly show direction. What do I mean by that? I mean that it's not enough to simply draw a coordinate system, let's say. Let me draw one here. So you have a coordinate system, and then it's not enough to just put a force in here. Let's say this is my F1, and then to show the components, you would, let's say, use these dashed lines, and that is often where students stop, but that is not enough. You have to clearly show in which direction they move. So for example, you have to understand that this is going in this direction and this is going in this direction. And so to properly name this here, this would be F1Y and this would be F1X. So that has to be clearly shown. So in other words, when we talk about clearly show directions, you have to provide arrowheads in any direction, not just if it coincides with the XYZ direction. It does not matter. You always have to show the arrowhead, even if it's like a diagonal line or whatever you have in your diagram. Always include that. And then, of course, you have to include the angles. Let's add that. So include angles. And in this picture here, it would be, of course, this alpha angle. That needs to be included as well. You, of course, also need a coordinate system. So must include coordinate system. So you need to provide a proper reference. So for example, here is X and Y. And then a few other things that can or cannot be part of your free body diagram, or that may or may not be part of your free body diagram. So for example, sometimes you have masses in there. So masses are represented by particles. Which of course is an idealization, so this is not true in real life, but it is representative of the mass and not the volume. We talked about this at the beginning. So ignore volume, only worry about the mass. And then you find that you have cables, of course, and those are represented by straight lines. Which is again an idealization. This is not true. So ideal. In reality, a cable always has self-weight, and therefore it's usually hanging a little bit through. In fact, that has something to do with Newton's third law, that you understand that the cable cannot be straight, because if the cable has weight, then it has to hang down. But that is something we don't worry about in this case. But let me very clearly state that cables can only be in tension and never in compression. And half of you are sitting there probably right now laughing about this statement because they think it's very clear, but you wouldn't believe how often this goes wrong. In fact, let me highlight this. So only tension is very important, because sometimes you may understand this physically and you would never answer this incorrect in your real world examples, but when you run numbers you sometimes forget it, or students sometimes forget this. And I had a teaching assistant once who said that the students always come up with a compression cable. They came up with like a new invention called the compression cable. But I encourage you to take any cable, take your USB cable that's probably laying right next to you right now, and pull on it, and you will see that it will resist. But as soon as you push on it, it will not provide any resistance. And that should be clear. And when we talk about the next example, or the upcoming example, I will come back to that statement, because it's so important for the interpretation of the free body diagram and all the drawings that you will complete. You also find sometimes springs in your free body diagrams. So springs, which we have a whole lecture dedicated to upcoming, but just so that you're aware here, since we're talking about free body diagrams, a spring would look something like this. This is not a resistor. So this would be a spring, and a spring usually has a spring constant. Called K. And we will have a whole lecture devoted to how to interpret this and how to deal with the spring constant and such. You will also sometimes find that there are pulley systems. And for those pulley systems, please understand that they only redirect the force. Only redirect the force. So they don't add or subtract any force. So let's say you have a pulley here that is hanging on the ceiling, and you have a force in a cable that's going in this direction, and let's say you have a box hanging here. Then the box, of course, is attracted by gravity and it wants to pull down, and there's tension in this part of the cable here, and that is no different from the tension here. So those pulleys only redirect the force, they don't change the force. That is very important to understand for some problems that you solve. Now let's, just for completeness reason, draw a proper free body diagram of all these conditions. I'm going to leave the springs and the pulleys out, but let's just draw a force system that is, let's say, a force going in this direction and a force going in that direction. And then we have a force pulling down. And now I'm going to call this here F1. And then there's a force F2 and F3. And this is sometimes the free body diagram that students present to me when I ask them to draw a free body diagram in an exam. And of course, that is not enough to get, let's say, 10 points. So the first thing you need is a component for each of these forces. So let's do that. And remember that when we draw components, we always have to include the direction. So let's say this and this and this. And we need to include names: F2y, F2x, F3x, and F3y. And that is still not done, because remember, we need to include angles. So let's call this alpha and this beta. Of course, you use numerical values there sometimes. But now we're still not done. We need a coordinate system, and it does not matter where you put the coordinate system. So I'm going to draw two for you here. Some students prefer to put it here and then have the y-axis here. That is acceptable for sure. And what often students prefer. However, an alternative would also be to put the coordinate system somewhere here in the upper right corner, and that needs to be included. So x, y, either one of these will work. Now let me explain to you real quick how I now, with this completed coordinate system, design my point system on exams, for example. So let's say you are asked to draw a free body diagram for 10 points. I will then look at it as complete and I will deduct points for everything you miss. So let's say you forget to name this F2, you lose 1 point. Let's say you forget to add the arrowhead here, you lose 1 point. Let's say you forget this vertical line, you lose 1 point. This is 1 point, 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 and so on and so forth. Don't worry, when you count this through, you will find that you can actually end up with negative points if you start with a 10-point problem, but that I do not do. So, but it's very common that when students only draw this line here, or these lines that they are used to from previous classes, that then they get like 0 points or maybe 2 points just for effort. That was pretty much non-existent. But understand that each of these makes a point in the exams. Please keep that in mind, because it's points that are so easy to make and where you do not have to lose anything. All right, before we move on to actually apply all these rules and to make use of our free body diagrams and equilibrium conditions and equation, let's talk about one important thing that relate to these free body diagrams. And that is that it is actually an idealization. It represents the physical world, but it is not the physical world. So what do I mean by this? Often I see students actually dealing with this from a real life perspective. So let's redraw the system as it would look in real life. This here with my 3 forces. Let's say I have a force here, and then my F2 is acting in this direction, and my F1 is going downwards. And let's say it is a traffic light that is hanging on the wall. So that would look like this. And for better interpretation, let's now give them names. So let me call this here node A, this is node B, and this is node C. And now the students have to draw the free body diagram, and I'm nice enough to always say for node A. So I ask them to draw the free body diagram for node A. And if they were to draw this, which they sometimes do, in fact, let me show you how they sometimes do it. They just go in and draw it like this, and they have not understood that this is not a free body diagram. A free body diagram is what you see here, which is actually node A released. So let's talk about that on conceptual level, so that you understand that this here this I call a cut cloud, and really what this is node A, right? So it's node A, the one that I have right here. And I released node A from the entire system, and I did not include whatever is going on here and here and here. So that is important to understand for a reason that I will explain to you further in just a second. But for now, let's continue to understand that this is a released node, and this has no dimensions, right? So this part here can be 5 meters long, it can be 10 meters long. It doesn't really matter for this picture to be true. So what I mean by that is my cut could actually be represented by something as little as here. So I could release it there, or I could even release it here. And that does not make a difference to my cut cloud that is given to you here. And now if we understand that, we are actually ready to understand the concept that is on the heart of this lecture, and that engineers use to really always determine unknown forces. So how do engineers really get to the point of calculating the tensile forces in such cable structures, let's say for a traffic light? So they draw this free body diagram, and what they really do is they include the known force. Let's say the traffic light has a known weight, F1, and then they don't know what F2 and F3 is. But they know that you have to pull back, you have to pull upwards to get that done. So let me develop this for you one last time. So I'm going to draw the free body diagram one more time, but now with the concept of let's find the unknown forces. So I initially have a cable that hangs in this direction. I have a cable that hangs in this direction, and I have a cable that is acting downwards. And now I know as an engineer what the force usually is, because this here has a mass, right? And you can multiply that by gravity to find the force. So this can turn into a force. And I can know that force. And because it's acting vertically downwards, because it's going in this direction, I know what that is. And let's pretend for a second that it's just 1 Newton, right? So let's say it's 1 Newton. Whatever it is, doesn't really matter. And the question is, hey, how do I find the force in this cable and the force in this cable? And I, as an engineer, just provided the cut, right? So I cut this off. That is where I released my node A. And what would happen in real life, you can really visualize this by thinking of these 2 strings or 2 cables, and there's 1 Newton hanging on it, and then you take a pair of scissors and you cut them. What happens? The whole thing falls down because there's 1 Newton acting on it. But for it to not fall down in real life, the engineer has to provide as much force in this cable and as much force in that cable as it was originally provided before it was cut. And by that I mean this state here. So here you see the entire body where the support here and the support here really keeps the tension in the cable. And if I cut it here, let's say, and I cut it here again, the system would fall down, and therefore it would not be in balance. So the engineer brings it back into balance by actually adding that force. And it's an unknown force, right? So here we call this F3 and this F2. And F2 and F3 is really the force that is actually acting in this cable. And the trick that we use is the free body diagram, and then later on the equilibrium equations, to really calculate how much force must be in this cable and in this cable for this node not to fall down, right? Remember, this is node A. And the reason I'm repeating myself here over and over again and explain this one more time in a free body diagram, the real world, and then developing the free body diagram, is because this concept here, where I cut it first and then I bring in the forces, is so important, because that is the trick that engineers always use. So engineers really always check, like, what happens if I remove the force that holds it in place. So before I drew this F2 on here, I had nothing acting here that moves in this direction, and therefore it actually would fall down. The whole system would fall down. And so my trick was, I removed the force really, and then I brought it back in. And this is the real concept that we're going to do so many times when we start actually calculating support reaction, like how much force is acting here on the wall, and so on and so forth. We will first remove the forces that we don't know, and then we will calculate or analyze how much it takes to bring it back into equilibrium. And that is an important concept. And the last thing we really need to understand what free body diagrams do for us and how they relate to the equilibrium conditions and equilibrium equations. So to close that circle, here you see this picture on the previous page where we have everything in the x direction that needs to be in equilibrium and everything in the y direction that needs to be in equilibrium. And we can use this free body diagram now to complete our equations and to then analyze the systems using the equilibrium conditions. So let's move on to examples. So here we can see our very first example problem for free body diagrams and for calculating forces in cable structures. As always, the first thing for us to do is read the problem statement, and we are asked to draw the free body diagram for node A. Again, I'm nice enough to say that. Often you just have to solve it, but this actually leads you to the solution. Because afterwards you need to determine the tensile forces in cables AB and AC. And for this problem, we need to assume that the box actually has a volume of 3.5 cubic meters and is filled with water. And that is probably a good starting point for us to think of 3.5 cubic meters of water. And before I convert that into a force for us, let us remember that in this class, gravity is always given with 10 meters per second square and not 9.81 meters per second square. So this is different from your physics class that you used before, but this would be too precise for engineers, at least when we look at structures, because we're really pretending a precision that we don't have. And the 10 meters per second square is always on the conservative side. So if we use this, the 10 meters per second square, we remember that 1 liter of water is equal to 1 kilogram. And we also remember that 1 kilogram is really equal to 10 Newton, which comes from the fact that 1 Newton is really equal to 100 grams. That is very basic information that is covered in the very first lecture. However, you remember this, and therefore you can convert the 3.5 cubic meter of water into an acting force. So 1 cubic meter of water is really equal to 1,000 liters, right? And 1,000 liters times 1 kilogram is equal to 1,000 kilograms. So that means that we now have to multiply this by 10 to get to Newton, right? 1 kilogram is 10 newtons, so we're now going to multiply that. So therefore, that is equal to 10,000 Newton, which is really equal to 10 kilonewton. And the way engineers say that is that water really is 10 kilonewton per cubic meter. And so therefore we now understand the weight in this box is actually 35 kilonewton. But we could solve this problem with any force acting on it. That's not the point of this. This was just giving us an educational starting point here, and it could reinforce our understanding of the water concept. I encourage you to think about this also in the imperial system. Of course, in the SI system, 10 kilonewton per cubic meter, that's a very easy number and is very useful. And you will see many problems like this in this class that relate to water. So please also understand how this works in the imperial system. And maybe just for your notes, I can tell you that water in the imperial system is what? 62.4 pounds per foot cubed, right? So I'll tell you that much, but you need to know how to interact with that and how to use that. I just showed you how this works in the SI system. But again, this is not relevant to solving the problem. This just gave us an educational opportunity here to bring this in, how real engineers deal with this thing. Now it's our job to draw the free body diagram, including that force. So let's really cut or release node A, because that's what we're asked to solve for. And then we'll pull out our ruler, because every time we're asked to draw a free body diagram, we always use straight lines and we always do it with a ruler. So I have to perform properly. And then I take the sloped line from above and I draw that portion. Then I draw the other portion. and of course my weight hanging on the system, which is acting downwards with, as we said before, 35 kilonewton. Now, remember that we released and we really cut the system here as shown above. And right now the system would fall down, so I have to pull on the cables to bring it back into equilibrium. But the question is, by how much do we have to pull? Let me call this here AC and this here AB, because that's the naming of the cables. And again, here is node A. So now I can use that to draw my complete free body diagram, because remember, we need to include all the important components. Let's start with the actual horizontal and vertical components. So for example, the horizontal components for both of these and the vertical component. And the direction. That would otherwise lose a point if I don't do that. And then I need to give proper names. ABX, ABY, ACY, and ACX. Almost complete, but not yet. So we have to include our coordinate system, which I'm going to do right here, just randomly somewhere within the drawing. Of course, I could also do it right on top of it, or a lot of students choose to do it here, like to put the origin of the coordinate system right at node A. That is absolutely correct and acceptable, but I just choose to do it differently. And now we need to include our angles, and look at the picture here. The angle is really given with 76 to the horizontal, so that means here to the horizontal it's also 76. So I'm just going to use that. So, because it's an enclosed angle here, so let's call this here 76 degrees. And then for the other one, I don't really need degrees, because it is the 12, 5, 13 triangle, which always creates a right angle here if you have such lengths. We explained that before. And this again is an educational opportunity for us to practice this. But this now is my complete free body diagram, which now I can use my equilibrium equations and conditions to solve. So let's first write down what we're after. So I'm going to start solving f of x is equal to 0, all the sums of the forces, and I'm choosing to have everything positive to the right. So what that means is that we're looking at plus AB, so 0 is equal to plus ABX minus ACX. And that is everything that's acting in the horizontal or the x direction. So I can move on to my next equation, which is the sum of the forces in the y direction being equal to 0. And that is upwards positive. And therefore we have plus ABY plus ACY and minus 35 kilonewton. And that is technically Newton's third law, and it is already complete. However, we cannot solve this, and let me explain that to you. You see two equations with how many unknowns do you see? Exactly, we'll see 4, right? We have ABX, ABY, ACX, and ACY. So this cannot be solved. Some students try that, but obviously you remember this from your basic math classes, that if you want to solve two equations, you need to do it with two unknowns. So what is the workaround here? I encourage you to think about that. The workaround really is that you can express ABY and ABX by one and the same unknown, which is AB. And I'm going to do that for you in a second. Likewise, AC can be used to express ACY and ACX. And so that's why I left some space here. Let's go ahead and do that. So I need, of course, access to my image here so that I can write 0 is equal to ABX. So what is ABX? ABX is really AB multiplied by 12 divided by 13, right? 12 over 13. And again, this is positive. And then I have to subtract my ACX, which is AC times the cosine of 76. So what I've done now is I expressed the horizontal component ABX in terms of the triangle here, and my ACX is expressed in terms of the cosine. And I'm going to do the same thing now for the vertical direction. So 0 is equal to plus AB times 5 divided by 13 plus AC times the sine of 76 minus 35 kilonewton. And those are now two equations with two unknowns. So check it out. I have AB as an unknown in this one and AB as an unknown in this one. And then likewise I have AC and AC. So I can now go ahead and name them. Let's call this here equation 1 and this down here equation 2, which of course we all learned somewhere in high school or in other math classes how to solve two equations with two unknowns. But my general teaching philosophy is to show you at least once what I ask of you so that you can see where I'm coming from and where I want you to go with this. And also students just have different backgrounds in these classes, and I want to get all of them on the same page. So let's get started and rearrange first equation 1. So let's write that down. So rearrange which then turns out to be, let's say we'll solve it for AB. So AB is nothing else than AC cosine of 76 multiplied by 13 divided by 12. And that is my very first equation that is solved for AB now. That means that I now substitute that AB into my equation 2. So now I'm going to call 1 into 2. And so my equation then would really read that I have 35 kilonewton. I bring this to the other side, right? This is negative in this case, so I bring it over, is equal to AB, which is nothing else than AC times the cosine of 76 times 13 divided by 12. Now be careful, often students forget that this has to be multiplied by 5/13 now. So let's go ahead and do that. Multiplied by 5/13. And because AC is a common term now in this equation, I can just bracket that out. So that was that, plus AC times sine of 76. And that is actually the entire equation. So now all I have to do to solve for AC, so AC is really equal to 35 kilonewton divided by whatever we have here in the brackets. So that would be cosine 76 times 13 over 12 times 5/13, and of course the 13 actually cancels out, right? So we can cross those out, plus sine 76. And that will give you the final answer, which is nothing else than 32.68. And that of course is in kilonewton, and it is a result, so I better double underline it. And I, of course, also should provide my answer arrow, right? And now I have the answer to AC, which I can now substitute back into my original equation 1, which then will give me AB. So what I'm going to do next is I'm going to take this value and substitute it back into here, which then means that I have 32.68 times cosine of 76 multiplied by 13/12, and that actually gives me a value of 8.564. And that is also in kilonewton. And it's a result. So my answer arrow needs to be provided. And last but not least, I can of course not just blindly trust these values. I am an engineer, so therefore I have to check my results. And how can I do that? I can of course check if these conditions are really true now. So let's go ahead and plug those values, for example, back into the original equation here. AB times 12/13 minus AC times cosine. So let's go ahead and do that, but I'm going to write that on the very bottom. So I'm going to call this a check. And my first one would be AB times 12/13. So AB would be 8.564 kilonewton multiplied by 12/13 minus AC, which is 32.68 kilonewton multiplied by the cosine of 76. And if I type that into my calculator, I end up with 0.0007 something, which effectively is 0, at least for engineers. We don't care about those precisions. In fact, that's why we're using 4 significant figures always. This is 0, and some of the imprecision actually stems from the fact that we used cosine and sine, and your calculator internally rounds these things. If we only were to use fraction, we actually would end up precisely with 0. We of course should still check our answer so that we definitely can get that A on the exam. So let's further check it, and let's run the other equation as well. So now I'm going to use the sum of the forces in the y direction, where I'm going to use 8.564 kilonewton, and I multiply this by 5/13, and in this case I add the 32.68 kilonewton, which then is multiplied by the sine of 76, and that turns out to be 35.00 something, I think 3, but again, this is something we don't worry about, therefore we are correct. We now have properly solved the problem, we have even checked it, and if you would have done this check on an exam, which only half the students always do, then you would know for sure that you are correct. So let's take a look at this picture again, at the overview, and let's understand that we solved the free body diagram problem. We used then the free body diagram and set up our equations. We moved from equations with 4 unknowns, right? So we had 2 equations with 4 unknowns that we then expressed with the same 2 unknowns, A, B, and AC, so that we have 2 equations with 2 unknowns that we then can solve by using substitution methods that I showed to you down here. And I just had to rearrange it to end up at my answer. And ultimately, I want to run a check. That's why we're engineers. We always check it. Nobody will tell us if it's right or wrong. We have to determine that ourselves. So I check my answer and I validated that this is correct. I believe that concludes this problem, and we can conceptually talk about the one on the following page. So here you see another example problem where you have to draw the free body diagram for node B in this case, right? So node B is given to you here. And we have 2 sub-problems here. I want to ask you to solve this for 2 different weights. For the first case, I would like you to think of it as the traffic light with a mass of 150 grams, which of course is way too little for a real traffic light. But it is giving us an opportunity to practice our engineering understanding if then in the second problem we do it for 250 grams. And I don't have to solve this problem for you because it's very similar to what you've seen before. Just that here now you're dealing with 2 angles. I will, however, give you the answer, and the answer for at least the first problem, would be that the force in AB, so let's call that FAB for 150 grams, would be equal to 1.272 Newton. And then FAC for 150 grams would give you a value of 0.531. 0.531. So that gives you a chance to practice this. And I really encourage you to do that so that you can use your knowledge that you developed in this sub-problem number 1 to come up with a smart way to quickly answer problem 2. So my best advice to you here is work smarter, not harder, and think deeply about the answers that led you here, or think deeply about the process that led you to these answers, so that you can then find the most quickest way to arrive at the solution for problem number 2. And of course, I don't want to give this away here. I want to encourage you to really think about this. So while I think this is very important, I don't want to tell you how it's done, because it's a very important revelation in your engineering education. So go ahead and calculate that. And if you don't find an easy way, if you think it's just as complicated as you solved for this, then I will encourage you to also find the solution for, let's say, FAB due to 200 grams, and also for FAC due to 200 grams. And then look at the ratio between the two. So compare this one to this one, and compare this one to that one. That should give you a very important engineering tool if you really understand how those results relate to each other. And that is, I think, everything I want to tell you here to keep your curiosity up and to also encourage you to solve this problem on your own. With that said, we have done enough examples for the free body diagrams and the equilibrium conditions and equilibrium equations. So let's move on to our homework problems. Of course, before we talk about homework problems, let's remember what we learned. So please ask yourself, what is your takeaway really from this class? But more importantly, as I always tell you, think about what's not clear to you and how you can actually improve your knowledge about the things that are not clear to you. Only if you understand what's not clear to you, you can actually make an improvement. So please go ahead and do that. Last but not least, let's check off our final checkpoints here. So first, we of course understand or recall Newton's third law, and we know what force equilibrium is. That was definitely explained in this lecture, and we now understand where that's coming from and why we need this. Then we talked about equilibrium conditions, and that is very important to be differentiated from the equilibrium equations. And we did this, of course, in 2D. So we understand the difference for those and what they are. Likewise, we talked a lot about free body diagrams, and we can now understand every significant component, and we know how they are to be interpreted. In fact, we can definitely professionally draw them now, because we know how to include all important components and aspects. So that is done too. And then, of course, we used these free body diagrams to derive our multiple equations, which we can now solve, right? So by using multiple equations with multiple unknowns, and we learned the substitution method, but really any method really works. So we can definitely solve multiple equations with multiple unknowns. And I believe that this overall goal of the lecture was to really understand how cable structures carry forces and how we can solve them. So hopefully we can check that off. And remember that we're only talking about tensile forces, so that we understand how they are transferred within a cable system. So that gets a check. And last but not least, we can definitely solve them for like real world examples So I think we had real world pictures that we used to derive the conditions and the equations, and that concludes our final checkpoints. So I wish you good luck with that, and hopefully you can check off as many boxes as I can here. Let's talk about the homework. As you can see here, we start the homework with very basic problems, just like idealized problems, if you will. In fact, the free body diagrams are already given to you. So here you have to pretty much make sure that this particle at the origin remains in equilibrium. So you have an FA and an FB, and you have F1 acting in this direction. Angles are given here to you, so this should be solvable for really every student in the class, independent of the different variables. Let's move on to the next problem. So problem B here is also a particle problem where this particle at the origin has to remain in equilibrium, and you have to substitute your values here and find FA and angle theta such that the system remains in equilibrium. Now, it may be the case that some students have such a strange F2 relative to F3 that this problem cannot be solved, although this would be very, very unlikely. But there may be 1 or 2 students who cannot do that based on their variables. If that happens to you, then you, of course, have to show and explain why that is the case. But I believe that this, for 99% of the students, should be solvable. Let's take a look at the next one. This becomes interesting now. Here you will see a gusset plate, which is a very famous structural component when we talk about trusses. You don't have to understand this here right now, but what you see is that there's one point of origin, which is the point where all the forces meet. And notice here that this is different from cables actually, because here you can also have a compression force. So notice that the 15 kilonewton here is actually pushing on the origin here, and so is the 10, whereas FB and the 5 kilonewton is actually pulling away from it. So please understand that that has an impact on your free body diagrams, in which direction you draw them, and also in, of course, solving the problems. But you have all the tricks you need to check your work. So I wish you good luck with that problem. And then here is another real world problem, if you will, where you have a boat that is attached to a bridle system, which then is anchored to F4. So there's a force of F4 acting in this cable AB, because the boat is pulled away from shore, or from the anchor point, I should say. And therefore, you can calculate what the forces are in BC and BD. And please understand that this is actually a planar system. So don't get confused by this seemingly 3D picture, right? Obviously it's attached to the boat in different locations and it's like somewhere random in space. However, A, B, C, and D are all acting in the same plane. So you can definitely solve this problem. And I believe that concludes an overview of the homework and provides you with all the information that you need to solve equilibrium of particles. I wish you good luck with your homework. I'll see you in the next lecture. Stay safe.